Okay, recall that a parallel plate capacitor consists of two conducting plates, one of which has a uniform charge distribution plus sigma, another minus sigma. And let's assume that sigma itself is positive, so that this is the positive plate and this is the negative plate. If we look at these plates from the side, we recall that we get a field 2 pi k sigma repelling from the positive plate and attracting toward the negative plate. The fields out here cancel. The field in between reinforces, and we end up with the field 4 pi Ka between the plates of the capacitor. Now what we want to do is calculate the voltage between the plates of the capacitor. Now what's the voltage? It's the energy per charge as we move across the plates. If we move a test charge Q from one plate to the other, let's say from the negative to the positive plate moving against the electric field, we'll do positive work. If we go from the positive to the negative with a positive test charge, we will have to do negative work. The field will do positive work on the charge. Okay, the delta W, the work done is just going to be force times delta S. The delta S is the distance from one plate to the other. We call that D here. So delta S is D. So that the work done in moving from one plate to the other is 4 pi k sigma times QD. Now that would be the work done on a positive charge by the field if we had it here and let it move here. Alternatively, the work that we would have to do to move a negative charge from here to here. To move a positive charge from here to here. It's the work we would do. Let's say that again. It's the work that would be done by the field to move a positive charge from here to here. It's the work we would have to do to move a positive charge from here to here. Voltage is just work per unit charge, so we divide the delta W between the plates by Q, and Q cancels out. We end up with 4 pi k sigma D. And this is the voltage between these two plates. And of course that's just the electric field times the distance. The 4 pi k sigma is the electric field, D is the distance. We never needed the charge, the test charge to start with, of course, since the electric field is what we get when we assume a test charge. So we could have gotten the voltage just by doing electric field times distance, but I wanted to go back and build this all up from the most fundamental concepts. Now if we have a charge Q on a parallel plate capacitor, two plates of area A separated by distance D, we can find the capacitance. What's capacitance? It's the ratio of charge to voltage. Capacitance is Q over V. Now how are we going to get, we've got Q. We've got Q sitting on these plates. How do we get V? Well, we just saw how we get V using sigma. V is 4 pi k sigma times D. What's sigma? Well, sigma is just the charge per unit area. Divide the charge by the area. Sigma is Q over A. So the V is going to be 4 pi k Q over A times D. And when we divide Q by V, then we're doing this calculation, and we end up with A divided by 4 pi k D, which could be written as 1 over 4 pi k times A over D. The 1 over 4 pi k is just a constant, and you can figure out what that constant is. Something like 9 times 10 to the negative 12th Coulomb squared per Newton meter squared. And A over D is just ratio of area to separation. Okay, now capacitance is charge over voltage. That means if we have a large area and a small separation, we get a lot of charge per volt. We can store a lot of charge per volt here, so it's to our advantage, if we want to store a lot of charge, to have the plates close together and to have a large area. We can accomplish that. You saw a while ago, if these had been metal plates, okay, put a piece of paper, which is a fairly good insulator, in between the metal plates, and we have a pretty good capacitor. Now these are plastic, not metal, so it's not going to make much of a capacitor. It wouldn't make a very big capacitor to start with. Alternatively, we can take metal. Okay, here's a piece of aluminum foil. We can make a perfectly good capacitor out of this piece of aluminum foil and two pieces of paper. I say it's a perfectly good capacitor. It's not going to be a very large capacitor, but I can take this foil, put it between, sandwich it in between two pieces of paper, smooth everything out, and curl it up. Okay, here's one end of the foil sticking up right here. Here's the other end of the foil sticking out here. I could put a lead here and a lead here on the foil. See if we can get that foil to stick out a little bit. There's a tab. Okay, so I could put a lead here on this tab and a lead here on this tab, and I'd have a parallel plate capacitor. A piece of paper is about 0.1 centimeter thick. If I could coil the paper very tightly about that foil, don't know how thick the foil is, but I would have a plate separation on the order of 0.01 centimeter. And then whatever area of the foil I have, actually I did that wrong. I sandwiched one piece of foil between two pieces of paper. It should have been a piece of paper between two pieces of foil. So my demonstration didn't work so well. I should really grab another piece of foil, but I don't have one handy, so I'm not going to do that now. I might come back and do that in a minute. Okay, anyhow, by doing that, we have a small separation, and the more foil we put, the more area, so the greater the capacitance would be. Now, in a minute, we'll calculate some examples of the capacitance, of capacitors that we could make in this way, and then we'd maybe talk about how people really make capacitors to make them very powerful, or very, to have a very high capacitance, to have a large charge to voltage ratio.